Hello, my name is Victor Moreno. I'm a product manager with the cloud networking team at Google. I'm going to talk to you a little bit about the role of networking in supporting AI inference. We'll explore traffic routing innovations, deployment patterns, and hopefully leave you with some good food for thought. When it comes to AI and ML workloads, networking plays a role in multiple surfaces: data ingestion, training, and inference. We will focus on inference today. At the foundation are high-performance GPU and TPUs with networking designed for minimal latency, maximum throughput, and no packet loss. This is enabled by technologies such as RDMA over Converged Ethernet, GPU direct kernel, and CPU bypass, and titanium offloads to have GPUs talk to each other or access storage. Our focus today is on AI-aware traffic routing optimizations to scale out the model service. Once you have optimized the GPU communication to create your model replicas, how do you optimally balance the traffic across those different model replicas or even different models so that you can optimize GPU or TPU utilization while delivering the best possible response to model consumers? Let's look at some of the common objectives when serving models for inference. You want to optimize the user experience and meet your service level objectives. You want to optimize the utilization of GPUs and TPUs to minimize the cost of accelerator idle time and also reduce the number of GPUs required. Load balancing on effective GPU metrics and knowledge of past computation is key to keeping GPUs saturated and reusing previous computations. An optimized network that accelerates loading models from storage into GPU memory to minimize cold start is key to enabling viable autoscaling. One interesting area where the network plays a role is in improving developer velocity by having a unified API to access any model. Developers can actually write their code once and change the target model with a simple variable change. No rewrite of code, no revision of the API calls. Streamlined A/B testing and agile iteration are simplified. The network is where these APIs can be normalized. And last but not the least, governance. Enabling governance and enforcing separation of concerns is nothing new to the networking team. Just like we deploy firewalls for centralized and unified policy enforcement, the network can insert services like AI guardrails to enforce responsible AI and also enforce authentication and authorization of APIs with API management platforms. Let's look at the network pattern. At the foundation, we have model replicas. A model replica is basically an instance of the software that can fulfill an inference request. A replica consists of an inference server that orchestrates running the prompt through the model across one or more GPUs or TPUs, and multiple nodes for larger models. Whether the replica has one node or multiple nodes, it is considered one replica. A replica will have a set capacity and can actually handle a certain volume of requests. Beyond that capacity, we scale out by creating multiple replicas, no different from what you would do with a traditional application. Now, to scale out across multiple replicas, we need a load balancer to actually route the traffic to the different replicas. What's special here is that the metrics that we would use to actually scale across replicas are very specific to AI, and the algorithms that we're going to use to choose the replicas are also very specific to the AI activity. To handle this, the load balancer is augmented with an inference scheduler to implement algorithms that are drastically different from what you would do with a regular load balancer. The open source community has defined the AI inference-specific traffic steering optimizations and components in the inference gateway architecture. The GKE inference gateway offers the functionality as a managed service. Once you have these replicas scaled out, you'll have different form factors. For these, you'll be consuming some models that are offered as a service, and you have no control over how the replica scale-out is done, or you'll be consuming other models that already existed on-prem or were deployed in a serverless form factor. Routing the traffic to the different models in the different form factors is done by yet another layer of load balancing, the front-end load balancing layer. There you would do model routing based on the API call. The load balancer, with the assistance of a body-based router extension, will choose which model to route to. You would also implement service extensions that allow you to seamlessly insert API management tools like Apigee or AI guardrail tools like Model Armor or NVIDIA guardrails. And this is the layer where we actually do the normalization of the API so that you can use one API to access all models. Let's talk about replica picking. Traditional workloads handle jobs that are uniform in size. Load balancers distribute requests to different replicas using a round-robin algorithm that simply assigns requests to different replicas in sequence. CPU and memory metrics can be leveraged by weighted round-robin algorithms to avoid busier replicas. However, the picture changes dramatically with AI. Inference workloads are highly variable in size, and the metrics that reflect the ability of a GPU to handle new jobs are new specialized metrics. A round-robin scheme is no longer viable. A more precise algorithm is needed, leveraging metrics that are GPU-specific and reflect the state of memory spaces that get utilized in a very different way than they do in a traditional application. A GPU or TPU could be fully utilized, and that would not be visible with traditional metrics. So without the right metrics, a load balancer could blindly send traffic to replicas that are effectively congested. The inference gateway uses metrics like KV cache utilization. The key value cache is the memory in which the tensors for the prompt are stored while the response is being generated. Using these specialized metrics, the least loaded replicas are identified and stack ranked. Traffic is distributed to the least loaded replicas rather than using a round-robin mechanism. Traditional, even distribution of requests isn't effective, but it doesn't stop there. The load balancer also keeps a shadow copy of the prefix caches that are in every replica. A prefix cache is basically what's stored in memory from previous prompt processing. So if you have processed a prompt that is 80% similar to what is being asked, well, that's probably a match. And the inference gateway has the technology in place to identify that match and send the traffic to the replica that has already run through a large part of that computation for that particular prompt. That computation is known as prefill, and is one of the most expensive parts of the inference process. So the inference gateway can reuse prefill computations that have been done before and rely on the commonality of different prompt requests to reduce GPU utilization. The inference-specific metrics are also used for the auto-scaling mechanisms to elastically expand the capacity of our cluster of replicas. This results in an auto-scaling mechanism that is coherent with the actual model utilization. We're extending the set of backends to these load balancers to include multiple regions and multiple networks to automatically chase capacity across regions and across networks. Without this functionality on the load balancer, capacity chasing requires complex logic in the application. A very interesting case is the one of low-rank adaptation, or LoRA, where we have a base foundational model combined with multiple lightweight adapters that can fine-tune the model for specific subjects. For example, a base language model may have LoRA adapters for different languages: Spanish, German, English, French. You can have multiple adapters loaded in memory and enabled at the same time, all running on the same model inference replica. Other adapters may sit in storage, waiting to be dynamically loaded into memory when needed. The inference gateway is aware of which LoRA adapters are active and in memory on different replicas. The inference gateway can steer the traffic to the replica with active hot adapters and minimize storage to memory transfer churn that can induce latency when using dynamic low-rank adaptation. You may need to serve a variety of models, for example, 𝗬𝗲, Mistral, 𝗬𝗲, or Claude, and developers may want to call them with a consistent API. However, some of these models and inference servers may expect a different URL and path than the one specified in the common API chosen. For instance, developers may want to use the OpenAI API to call any model and include a model identifier in the payload of the request, rather than including it in the URL and path. For a load balancer to actually route based on the model identifier, it needs to do something that we refer to as body-based routing, and extract the model ID from the payload to trigger header mutations and drive routing decisions. Think of this load balancer as a surface, as it is globally scaled out with multiple instances and isn't a choke point as you would envision a traditional discrete load balancer. On this surface, you can actually insert other services, you can make callouts, or you can have plugins that are actually brought into the flow of traffic without you having to do any particular routing or topology changes. So you can insert API management tools without creating a northbound and a southbound network to topologically enforce traversal through the API management tool. We can use service extensions to insert services without changing the topology. We can also insert AI guardrails. These are just two examples of the type of services that can be inserted. But we can also include observability plugins or callouts. We could override headers. We can do all sorts of interesting things. So the extensibility of the load balancer can't be understated in the area of AI safety and security. One interesting service that can be inserted is semantic caching, which would allow previously generated responses to be reused and provide a very fast response without burdening the model replicas and incurring the cost of computation. One very important function to insert are AI guardrails to sanitize prompts and responses. When the prompt arrives, it sends it to a guardrail service like Model Armor or NVIDIA Guardrails to check if the prompt is within policy. Is the prompt appropriate? Am I asking about topics that shouldn't be asked? If so, the request is dropped and an error is returned. You don't even send the prompt to the model and spend the money on the GPU usage. But maybe the prompt is valid, but the response is encumbered with personally identifiable information or things that shouldn't be sent out, and then again, the guardrails take care of that when inspecting the response. There are two different network patterns that you may encounter. If all your models are built by your team in GKE and everything in the endpoint is basically GKE based, we could have the model routing, the insertion of the services, as well as all the replica picking optimizations be done in one layer of load balancing, which is delivered using the GKE inference gateway. This is the pattern that you see on the left. When using a mix of model form factors, expect the pattern on the right, where you actually split the model routing, insertion of guardrails, and API management into the top layer of load balancing, and then you would have underneath that a variety of different form factors. Some of these form factors are consumed as a service, like the vertex or public models, for instance. And you don't really control what's happening on the load balancer in front of those replicas. So you have two tiers of load balancing, and you split the functionality that we've talked about into those two tiers. In conclusion, the network plays a critical role for inference. Inference workloads required customized routing, so the toolkit of the past isn't just going to solve it today. Look into your options. Look into prefix-aware caching. Look into pre-filled decode disaggregation, which is coming soon. The network plays an active role in the normalization of APIs as well. And governance through service insertion is one of the expected roles of the network. Extensibility through service extensions is a key tool to address a rapidly evolving problem space. The development of this functional architecture is a focal area for the open source community and for Google Cloud. We can't do it without you. Join us in this exciting journey. Thank you.